So yesterday, we kind of continued on with vertical circular motion, but just the way the kind of calendar fell, I taught you a little bit on Friday, went over the rest of the nuts and bolts yesterday, but we didn't get, I felt, enough time to really get into problem solving, so I didn't think it was fair to quiz you on it yet. That's why there was no quiz posted. And I probably should have just said no quiz tomorrow, but that slipped my mind. So what I have on the board is a quiz, but wait for it, okay? It's not coming in for marks. I just want to use them as some examples. So what I want you to do is write them down, give them a try, and then we'll go through them together just as some additional examples. I'm not going to take it in. We're not going to mark it or anything like that. And then we're going to continue today, spending most of today working on just vertical circular motion problem solving. Tomorrow, you'll get your assignment on circular motion because tomorrow marks we're halfway done. Actually, we're more than halfway done this unit, which is why your exam date was posted. I think I forgot to tell you guys about that, but it'll be May 17th. Okay. We'll probably be done the unit before that, but I wanted to be able to give you the 2 weeks notice. So there it is. So tomorrow we'll do the assignment, and then after that we'll be moving on to gravitation, okay, which is the second half of the unit, and then after that unit exam, then last unit. Okay, so it's yeah, you can see the end now. Just so you know, the light at the end of the tunnel may be you. Okay, so for our first one here, okay, we're looking at the coefficient of friction of an unbanked curve. So obviously, what acts as the centripetal force for an unbanked curve? Friction. Okay, so here's what we know. We know that mu is, we're looking for mu. And we know that the radius of the corner is 85 meters, and the speed at which it can be taken is 12 meters per second. Okay, so because this is an unbanked curve, the centripetal force is being provided by the force of friction. Okay, it keeps you from sliding out, static friction in particular. So mv squared over r equals mu times m times g. I can just say the force of gravity because obviously the surface is unbanked, and as a result, gravity and normal force are equal. Okay, so mass is going to cancel, and we're looking for mu. So all we have to do is divide both sides by g, and what we'll have is that mu equals v squared over r times g. And so that'll be our 12 squared divided by 85 times 9.81. All right, so our coefficient of friction is quite small, actually. This is a fairly slippery corner. Okay, 0.17 is our mu. No units on that, and only 2 significant digits. Okay, going over the top of a vertical circle. Okay, so first thing we need to do is we need to identify our forces. Okay, as we go over the top of a vertical circle, what's this force? Gravity. What's this force? Normal force. Which one's bigger? Gravity is bigger. It has to be. If it's not, this thing doesn't go, well, it doesn't do at all what it's supposed to do. Okay, it like literally flies off of the corner being like thrown off of it. That can't happen, obviously. Okay, so normal force is going to be less, and that's what they're wanting us to calculate because apparent weight is normal force. So what we know is the mass of the motorcycle, 160 kilograms. Okay, and we know the speed, 35 meters per second, and we know the radius is 235 meters. Right? That's what we have. So all vertical circular motion relies on this. Fc being the vector sum of all forces, in other words, in minus out. Okay? The force in is gravity, the force out is normal force. So we're going to have Fc equals force of gravity minus normal force, and I'm trying to calculate normal force. Okay, for me, I like to solve for things when they're positive, so I'm bringing it over to this side and then subtracting Fc. So we'll have Fn equals force of gravity minus centripetal force. So that'll be m times g minus mv squared over r. Okay, so we've got our 160 kilograms times 9.81, don't know why I put the units in there, minus 160 times, we're moving at 35? Yeah. Over 235. Okay, so when we punch all that in, so we'll have 160 times 9.81 minus 160 times 35 squared divided by 235. All right, so we are looking at an apparent weight of 7, what do we have for sig digs there? We had 2. So we're looking at 7.4 times 10 to the 2 newtons. Okay, does that answer make sense given the situation? It is certainly less than the actual weight of the motorcycle. Okay, so yes, it does make sense. The person should feel lighter traveling over the top of a vertical circle at speed. Okay? All right, is that making sense to everybody? All right, so it's just a matter of we got to remember and gain experience with using those concepts in different situations. Okay, kind of get the hang of doing the algebra to do with these kind of questions, and then seeing kind of how we sit with that. Okay, so in your digital workbook on the bottom of page 2 is where this stuff starts. We did question number 1 at the end of class yesterday, so you don't have to do that one. Okay, but the rest of these are all vertical circular motion problems. Okay, and I want you to give them a try, and we'll go through them as we go. There's 11 of them. I don't think that's going to take you all class. Okay, but I'll give you a little break in the middle. If you guys can get going on those, I will be happy to help you if you have any questions. Right, and certainly we can go over any that give us trouble. It's actually, I think you're saying, what's their apparent mass? Is that what you're saying?
Maybe.
Yeah, and that's actually something that comes up quite often, but you can have apparent weight because you feel weight, but you can't have an apparent mass because there can't apparently be less of you. Right? It doesn't matter where I go, my mass is the same. It doesn't matter how fast I move into a circle, my mass is the same. I never have an apparent mass. But sometimes people kind of look at it that way, and then some people even go as far as to calculate on a question like that, an apparent mass, and then I'll be like, okay, like you did everything right, you got the apparent weight, and then you did this extra calculation about apparent mass, which apparently you can't do, because, yeah, there can't apparently be less of me. I'm always gonna be the same amount of me, but I can feel different, and I feel forces, I don't feel my mass. That makes sense.
Yeah.
Okay, you got diameter, did you make it radius? Divided by 2?
Oh, I'm still getting the wrong answer.
Little trick, yeah. That's a dirty
It's
trick.
diameter, not radius.
I'm always.
Yeah, guys, watch out in number 4. Dirty trick. Okay, I give you the diameter, not the radius. You gotta divide that number by 2 to get R. So if you're not getting the right answer for number 5, or sorry, for number 4, that may be why.
Oh, a wheel-shaped space station is not a vertical structure. There's no gravity. Yeah, it's artificial gravity. So it's not a vertical structure.
The only way I know whether a circle is vertical or not is if I have gravity as a reference. If I'm out in orbit and things spinning around, I have no gravity as a reference.
This goes here, this goes here. Is that, even if there is no gravity, is that like the vertical circle?
Yeah, how would we do that one on 4?
No gravity.
Okay. Let's have a look at number 6, because I threw number 6 in there, you know, just because sometimes I throw in a question that's not like all the others. This one's not a vertical circular motion question, okay? I only know if I'm in a vertical circle if I have gravity as a reference, okay? Gravity can tell me, whoops, I had that running. Okay, gravity can tell me which way is up and down. Without it, I don't know. I don't have a vertical or a horizontal without it. It's because vertical and horizontal are reference to gravity. Okay, so if I have, sorry, a space station that's shaped like a wheel, okay, and I know its radius is 48 meters, okay, I'm looking for how fast it has to rotate. So I'm looking for the speed for the crew members to have the same apparent weight on this station as they would have on Earth. All right, artificial gravity looks like this. Actually, it looks like this. I want the normal force from the floor of the station to feel like gravity. Okay, that's why I substitute in the next step Fg for Fn. Okay, Fn is a reactive force, but its value is equivalent to gravity. Everyone okay with that? Okay, so then I just plug in my formulas. M times G equals mv squared over R. Okay, so Jenna, in answer to your question, I wasn't given the mass, and you're right. I wasn't, because everybody on the station, regardless of their mass, should feel like they're at home. That's why we leave G here. We're basically calculating the acceleration that would be produced. Okay, so in the end, what we get is G times R rooted, okay, to equal V, like we did with basically every artificial gravity question. So I guess the thing is, I put a question on a vertical circular motion worksheet that wasn't a vertical circular motion question, just to, you know, keep you from getting into a rut, okay, and just kind of go, hey, this one's a little different, because on a test, obviously, you're going to get all kinds of different questions. You got to be able to shift gears, okay? So I'm sorry if that frustrated you. Okay, that would be on me. I'm the one who did it. Okay. All right. So we got 9.81 times the radius, which was 48 meters. That was the only value we were in fact given. Okay. And when we do that, we should get 22 meters per second. Okay. Everybody all right with that one?
Well, attached to the edges. It's like this. Yes, like that. It would be very circular motion on the second.
So on a question like number 5, basically what we have is something being whirled around on a thin string. Okay? Now, where is that string going to have to exert the most force?
At the bottom.
At the bottom. That's where it's going to break. Okay? If it's whirling around, I keep going faster and faster and faster, it's going to break when it's at its maximum tension. And that maximum tension is 186 newtons. Okay, so it can exert 186 newtons worth of tension, which is the same as normal force. It acts up at the bottom of a circle. Okay, and we know that it's 1.9 meters long. So we know that the force tension, which is like normal force, is 186 newtons. Okay, we know the mass is 1.50 kilograms. Okay, and we know that the radius is 1.90 meters. We're looking for V. so bottom of the circle, normal force acting in, gravity acting out, or tension. I keep writing normal force, but I mean tension. Okay, so we got force, tension acting in. Okay, so Fc equals forces in, tension, minus forces out, gravity. So we got mv squared over r equals 186 minus 1.5 times 9.81. Okay, everybody with me so far? Right, I'm trying to find v, so I've got to bring m and r over. So I'm just going to bracket this so that it's clear what I'm doing. Okay, I'm bringing r over here, multiplying that side by r, and then I'm dividing that side by m. That takes care of those two things. Then I'm square rooting it, okay, to get my speed. All right, so speed equals, okay, I've already got it all written in there, so now we'll just punch in the numbers. Okay, so square root of, bracket, 186, minus 1.5 times 9.81 times the radius, which was 1.9, and then divided by the mass, which was 1.5. Okay, 14.7. Yeah, meters per second would be our answer. Okay, so sometimes a question, I mean, that's the trickiest manipulation you're going to get, okay, for a vertical circular motion question. But it also tests your understanding of vertical circular motion. Where in the circle is the strain most likely to break? Okay, and it's most likely to break where it's under the most strain at the bottom. Okay, that sort of makes sense? Okay, so sometimes a question's asking more than for just a number. It's also asking, do you understand how this particular thing works? Okay, so what we're looking at here, guys, really look at the point values on all of these problems. They give you a pretty good idea how much work is involved in the problem. It's a 3-mark question. It's like givens, formula, answer. Okay, like there's not going to be multiple steps or anything like that. Okay, the biggest thing to watch out for here, significant digits. Okay, so remember your significant digit rules. And there's a couple of questions where it actually says, like for question number 3, what is the magnitude and direction of the centripetal acceleration? We haven't put directions on anything thus far in this unit because centripetal tells you which way it's acting. Okay, all centripetal things are directed where?
Towards the center.
Right. It's just asking you to actually outright say that on your answer. Okay, I think there's 2 questions where it actually asks that, or maybe it's just one. But there's just watch out for it. Okay. Yeah. So like I said, 1 and 2, they're pretty straightforward. Okay. They're like the first things we went over in the unit. Calculating period, frequency, stuff like that. Then we got some centripetal acceleration stuff. So that would be 3 and 4. And then number 5 is a very basic centripetal force question. Okay. Same with number 6. It's also asking about the relationship between centripetal force and speed. Okay, so if we double the speed, what will happen to the centripetal force? We've talked about that. It's also what your lab is actually the reverse of it. The one that's due on Friday is the reverse. But just do the math and you'll see it. And then for number 7, okay, you got a bank curve. Okay, you got actually 2 bank curves. You got apparent weightlessness. You got vertical circle stuff. You've got artificial gravity in there, I think. No, there isn't an artificial gravity question. But yeah, we've done questions like basically all of these, so there's nothing there that should be surprising, really. All right, so just take your time, show your work. And if there's questions, I will give cryptic answers and hints, because obviously this is coming in from ours. Okay, I'll figure out when I want it to be here tonight. It's going to be May 9th, And that's simply because I totally believe you're gonna be done in class at some point tomorrow. Okay, I really don't think this is gonna take you very long, so, May 9th would be, that's Monday, okay, is the due date for it. I don't think it's gonna be much homework effort, maybe at all.
So you